I now want to get to rotation, and in order to do that I want to generalize a little bit, and I want to talk about linear transformations, and I'm going to drop one dimension down and generalize a bit. So, I'm going to, instead of going directly to 3D rotations, I'm going to talk about 2D linear transformations, and then I want to talk about the kinds of properties that a 2D rotation should have, because 2D is very easy for us to understand. Then when we understand those properties, we'll generalize back up to 3D, and we'll see some structure I think that's interesting that perhaps you haven't seen before. So, let's think about 2D linear transforms, 2D linear transformations. So, I will just have a 2 by 2 matrix M11, M21, M12, and M22, just 2 by 2 matrix with real valued entries, and I have a 2-dimensional point. So, instead of having x, y, z, I just have x, y. I'm writing it vertically so that we can perform matrix operations. Someone thought it was a good idea to write it that way, so we consistently do that in linear algebra. So, if I perform a linear transformation, I get, let's say, x prime, y prime. Right. So, in other words, I have some point x, y, and by applying that matrix I get some x prime, y prime, right. So, some kind of transformation has been performed. Again, we're just in 2 dimensions here. Let's write a 2D coordinate system, Cartesian coordinate system. So, I have x axis, y axis, and I want to think about simplest case. This is the point 1 comma 0 right here, and this is the point 0 comma 1. These are the standard bases that we use for Cartesian coordinates all the time. And I want to think about what happens to these when we perform our transformation. So, we have M11, M12, M21, M22. Let's transform this first point here 1 comma 0, right. So, if we transform that 1 0, so I put the point here, I look at what we get when we perform the multiplication, and we get M11, M21, right. So, I perform this multiplication and it drops off the second column. All I get remaining here is the first column by doing this operation. So, very interesting. So, it looks like when I perform this linear transformation, it tells me exactly what happens to the x coordinate axis, right. So basically this column here tells me exactly what's going to happen to the x coordinate. Is that right? Because I've just taken it exactly of length 1. I'm lined up perfectly with this axis. So, it's telling me what happens to this basis element, right. You may write these as I hat and j hat in engineering, and if there's a third dimension you may write these as k hat, right. These are just the unit basis elements for Cartesian coordinates when you start doing basic vector calculus, correct? So, I'm just saying that what happens is with a linear transformation, you may have seen this before, just pay attention that every column here is going to correspond to what happens to the coordinate axis in its particular place. So, the first column says what happens or indicates what happens, directly happens to the x coordinate. And if we do similar thing for the y coordinate, M1, let me write the matrix again, M11, M12, M21, M22, and now I put the 0 1 here. Notice how it just nicely selects, right. I've picked this point here, which is representing the y part, the y basis element. Then it just nicely picks the second column, 1 2, M2 2. Right. So, I just wanted to point that out, right. Just you may have heard this before somewhere in linear algebra. It's very, very simple in 2 dimensions to see it happening. So, each one of these columns just tells what happens to the corresponding basis element or the corresponding coordinate. So, if I think like this, then it's very helpful now to take some very simple matrices and look at what they do. So, let me just make some examples here. And again, I'm trying to set this up. I'm reminding you about basics of linear algebra, which most of you have seen before, I assume. but I'm also going to connect it a little bit later to something more complicated. So please bear with me if this is painfully simple. But I want it to be very clear, and then we'll get to more complicated things. So if my matrix now is this, and I apply it to my point x, y, should be very clear what happens then. Again, if I just look at these columns, if I apply this to 1, 0, it's no change, right? So if I take this matrix and substitute it in here, I apply it to 1, 0, it remains 1, 0. If I apply it to 0, 1, it remains 0, 1. Perfect. So this is the identity matrix, so it has no effect, right? Just think about how it's going to transform this space. So if I now put something in this space here, right? So I now put some kind of object in here, right? And I start transforming all of the points in it. So I can transform anything in this space here, including a simple triangle, of course. I just want to think about what happens to it. This one has no effect. Well, good thing. We call it the identity matrix. It should have algebraically no effect. Let's try another one. So what if I have 2, 0, 0, 2? Right? What will it do in that case? It just scales it, right? So this should stretch along the x-axis by a factor of 2, stretch along the y-axis by a factor of 2, simply scales it. If I pick 1/2 instead, it will shrink it, right? So it's a scaling of some kind. And of course I could put different numbers for different axes, and then I'll get different kinds of stretchings, right? I can stretch it out along one axis or another. That will distort, what do we call it? The aspect ratio when it comes to monitors and things like that, right? So it'll distort the aspect ratio. All right. -1, 0, 0, 1. So what will that give us? Right? So it's a kind of flip, right? So it gives us a mirror image, let's say, right? It's an informal way to say it. So we get a mirror image. Now that's not something I'm going to consider to be satisfying from the perspective of rigid body transformations. You should not be able to move a body through space and then say, ah, it's been mirror image now, right? That doesn't seem like something that happens, right? So this one's not going to be a legal kind of motion. The scaling is also not legal. When you move a body through space, it should not all of a sudden be a different size. So very interesting to think about. Let's try this one. Let's do a double mirror image. So what if I go and let's see here, draw a line here. So what if I do this? I do -1, 0, 0, -1, right? So what will that do? So if I flip with respect, or I do the mirror kind of flip, let's say a symmetry flip, if I do the flip with respect to the x-axis and then the flip with respect to the y-axis, after flipping twice, I've mirrored the mirror, which makes it unmirrored, and I've turned this object upside down, right? So very nice. So that actually is a rotation because it's upside down and it's not been mirror imaged. So this one is rotate by 180 degrees, which if we put our math hats on, we'll use radians. So rotate by pi. Right? There's some other more complicated ones which we do end up needing somewhere else when we get outside of rigid bodies. But what would this do? Right? If I apply this transformation. So now, for the x coordinate, it'll start increasing as y gets greater, right? Because x is going to get replaced by x plus y. So that will have an effect of taking something that is, let me draw it here. If I start off with a square, it will turn into something like this, right? So it's what is called a shearing transformation. So if I do this, I get an x shear. And if you want a y shear, you can just go the other way. You get a y shear, which will be stretching upward in the other direction. You can have combinations of shears of all different scales, and you can have mirror images. All of these things combined together is the power of 2D linear transformations, right? So the question now is, if I only want to apply rotations, what am I allowed to do? Let's just add constraints. Let's tear away or delete all of the things we don't like and see what's left. How many degrees of freedom do we have if we can make any 2 by 2 matrix we want? 4, right? Just 4 independent real numbers we can put in here. And so we have 4 degrees of freedom to start with. So I want to think about it from the elimination perspective. I want to eliminate degrees of freedom that I don't want to allow happening, and eliminate anything else I might need to beyond that, so that I'm satisfied that what I'm left with is just rotations. All right. So for rotations, again we're still in 2D. What am I not allowed to have? So I want no, I think it's very informal, no stretching of axes. In other words, I want to preserve scale. So let's start off. We have 4 degrees of freedom in this matrix, M11, M21, M12, M22, right? We have 4 degrees of freedom in that. And now I'm going to start imposing constraints. So constraint number 1 here, if I have no stretching of axes, that means these columns, remember I told you what that each column represents the distortion of the axis or the transformation of the axis, it must have length 1. Right? The column overall has to have length 1. Otherwise, if you think about it, right, the matrix multiplication is just performing a simple dot product or inner product. And so if the magnitude of the vector that you're multiplying with is not normalized, then you get a different scale. So it has to have unit length. So constraint number 1 here means that columns, so have length 1. So in other words, when I have this matrix, I look at the columns, and I must have the case that M11 squared plus M21 squared equals 1. Right, so I get this constraint. Right. And I must have this constraint here very similarly, M12 squared plus M22 squared equals 1. How many degrees of freedom did I just lose? 2. So I lost 2 degrees of freedom. So I had 4. Each one of these circles here, I'm like, you know, imagine I'm the professor marking off points here, right? Taking off points from your grade. So let's say you lost 1 for that. You have 1 degree of freedom less. You lost 1 for that. Now you only have 2 degrees of freedom left. 2, I want to have no shearing. Right? I don't like these strange shearing effect. That's not natural for rigid body transformations. So what it means in that case is that these coordinate axes here, right? Remember each one of these is the transformed coordinate axis. They have to remain orthogonal or perpendicular, right? So in basic, when you multiply vectors together using a dot product or inner product, what's the condition you have for that? What has to be satisfied for them to be perpendicular? 0, right? So that's the condition. You just have to say that these columns, when you take the inner product, right, because each one of these represents a vector by itself that says where the coordinate axis is getting transformed to, right, the coordinate basis is getting transformed to. So when I take these two and take their inner product, I get a constraint that looks like this. So this is the number 2 condition there, which is M11, M12 plus M21, M22. So just the dot product or inner product, these 2 columns, has to equal 0. How many degrees of freedom did I lose there? 1. Lost 1 degree of freedom. 1 nice constraint here, lost 1 degree of freedom. So let's say that one's minus 1. I hope we have some degrees of freedom left, all right, by the time we're done with this. Maybe we're done. Are we done? We got down to 1 degree of freedom, and you said it was, and you and I, we all agree that 1 degree of freedom was appropriate for 2-dimensional rotation. So are we done? Do we have all the constraints or not? We'll do this democratically. Who thinks we're done? And if the majority thinks so, then we'll just finish. Who thinks we're not done? The majority is not sure, I think. Okay. Well, there's one more constraint remaining. We got the number of degrees of freedom right, but we do not tolerate mirror images. Right? So we have to fix that. So after we impose these two constraints, the last thing I want to think about now is I want to say no mirror images. The formal way to say that in mathematics is you need to preserve orientation. So no orientation changing. If you don't pay attention to that, then your left-handed coordinate system can become right-handed. All kinds of bad things can happen, right? So we need to preserve orientation. All right, so no mirror images. After we perform these two constraints, it turns out that there's not very many options left for the determinant of that matrix. It can only be 1 or minus 1. So it ends up being a beautiful detector of whether or not someone's trying to perform a mirror image, right, by making that matrix. So the only thing you have to have happen for the remaining case, well, I'll write it over here, I guess, to implement that is determinant of the matrix. Put the whole matrix in. I'm just writing dots, but I should put the m's in there. Needs to be equal to 1, not negative 1. Those are the only two possibilities left. How many degrees of freedom did I lose there? 0. I didn't lose any degrees of freedom. So what's interesting is that what remains is going to be a circle of possible two-dimensional rotations. Before I did constraint number 3, I actually had 2 circles. There's a circle of the standard rotations, and then there's a circle of mirror imaged rotations. And so this last constraint just eliminates the bad circle, the circle that does not correspond to rigid bodies. All right, so that's the next kind of interesting question, is which matrices remain, right? Because these are going to be the ones that are rotations. So after I perform all of this, and in fact when I look at these equations here, that looks somewhat familiar, right? So if I, instead of writing m11, m21, if I just wrote that with x and y coordinates, you recognize this as the equation of a unit circle in the plane. So it's enough to just parameterize this circle and then derive the other 2 parameters of the matrix from the point on the circle. So that's what turns out to be fairly easy to do, and ends up working very nicely, so that if I do it in that way, then I can just parameterize the circle. So what I just said there, let me do it along here, then I just say m11 is equal to cosine theta, m21 is equal to sine theta. That's just a standard parameterization of the unit circle, right? Right, so I have standard parameterization of the unit circle, some amount theta. I guess my coordinate system in this particular case is the m11 axis and the m21 axis. Right, so that's all I've done. I'm just taking the first column here and showing that you can parameterize it nicely as a circle. So the matrices I get are cosine theta, sine theta, and now I just do simple substitutions to figure out from the algebra here in these equations in number 1 and number 2 to figure out the rest of it. I get minus sine theta and cosine theta, and you can do simple substitution up here, for example, to verify that constraint number 2 is just fine. You can easily see that constraint number 1 is satisfied for the second column, this one here, because it's still, when I square these and add them up, I get that famous trigonometric identity, sum of squares of sine and cosine is 1. So that happens for the columns. The inner product clearly works and adds up to be 0. So these are the matrices that remain, and a beautiful parameterization has been found by simple recognition that these fall onto a unit circle. So 2D rotation ends up being very easy for that reason.